And today we're looking at aerodynamics. We've had a fair amount of aerodynamics in your private ground school. You've had basic aerodynamics class. Some of you may have had advanced aerodynamics already. So we're going to be looking at aerodynamics from what do you need to know for commercial pilot knowledge exam preparation. It's also good information for when you're going into your commercial pilot check ride. And if you're going to be a flight instructor, this will be very good knowledge for you as well. I got a variety of topics today, and probably I'm going to go a little quicker than I normally do. If you miss something in the notes, I am recording the session, so you'll be able to go back and get a recording of it as well. Let's start off with some basic aerodynamics. And we have a discussion area for any of your questions. Let's just kick things off with knowledge of the basic lift equation. Well, this is the lift equation itself, and we'll kind of try to make it a little bit more basic for you. This isn't something I'm going to necessarily test you on knowing this formula, but using this formula will help you understand a lot of things with performance. And next time we meet, we'll be looking at performance as well. So we start off with our first variable being the coefficient of lift. Okay. So your wing shape produces a certain amount of lift. We're talking about an airfoil. Airfoil is a shape. And numerically, we can say that that shape produces this much lift. And when we take that airfoil shape and we start stacking airfoil shapes together, we start making a wing out of it that has a certain area to it. So now we have that airfoil shape, creates a certain amount of lift, multiplied by the amount of wing area that there is. And we can see how much lift that wing can generate. There are some variables in this problem. And those variables involve, first of all, rho, which is the air density that you're flying in, the amount of pressure there is, and your true airspeed squared. Now, understanding that these are variables can help us understand why certain performance factors affect takeoff distance, climb performance, landing distance. Keep in mind that in order to get a 3,000-pound airplane airborne, you need about 3,000 pounds of lift. Your wing shape at present technology here doesn't change its shape. They are developing that technology for later in the future, but for our purposes, the coefficient of lift, that's the shape of the wing, that's constant. Okay? Our wing area, okay, given the same configuration, flaps up, flaps down, okay, your wing area does not change. So those are your constants in there. Changing then is the amount of air molecules that you have to work with. In general, more air molecules per volume of air, better performance. Therefore, you can see that as you are closer to sea level, you don't have to get very much airspeed to get enough lift for that 3,000-pound airplane. However, you start going up into the mountains with a lower pressure. If pressure goes down here, then your speed must go up to produce the same amount of lift. So you can apply that right to takeoff. At takeoff, I really can't change angle of attack. I'm very dependent upon airflow over the wing. So as I go higher up in the mountains for a high altitude takeoff, I have to get a faster true airspeed in order to generate enough lift to get airborne. So those are going to be some things to keep in mind here. Let's think about lift development in terms of a couple of different principles, starting with Bernoulli's principle. Bernoulli was a scientist, lived quite a while ago, several hundred years ago, and did experiments with a restriction. Kind of had a tube with a restriction in it and found that the amount of airflow going through the tube, as it hit the restriction, that same amount of airflow, given that volume, it made it through the restriction. So even though there was a reduction in the area, Bernoulli found that the velocity of the air did increase, and also that the pressure of that air decreased going through the restriction. So this is Bernoulli's principle for lift development. Airflow is a constant given a certain volume of air, a certain number of molecules to it, a certain weight to it. So the pressure and the velocity are the ones that are going to be different in it. And the effect here that we take is that wing shape is generating an area where there's a restriction on one side of the airfoil. So hence a greater acceleration of the airflow over it. More speed equals more lift is what it boils down to here. I got some little videos here to help demonstrate that effect. Looking at this first one here, simply blowing over the top of a piece of paper. All this person's doing. That top of the paper is acting like a restriction. Think about the Venturi tube, it's acting like that restriction. And so we get an airflow over it that's accelerated. And you can see from this demonstration that there's actually a higher pressure underneath and a lower pressure on top. It's effectively how our wings are operating. You might ask the question, is the wing being sucked up because of low pressure, or is it being pushed up because of the high pressure beneath it? In general, it's the higher pressure beneath it that is pushing the wing up, because that high pressure is trying to get to low pressure. Got some other videos here to show you of smoke tunnel tests. We put a wind tunnel in with smoke lines, and you can see the airfoil shape here. We'll start running this, running at high speed here. We'll slow it down here. But basically, you can see that what your instructor told you, that the top of the airfoil will accelerate the air. As we get to the stagnation point here of the wing, we see a definite split, in that the airflow on top is definitely traveling faster than the airflow beneath it there. So yes, what your instructor told you is absolutely true with that. Okay. That acceleration of the air on top of the wing causes that pressure differential that lowers the pressure down. It also lowers the temperature, which could cause it to reach the dew point temperature, which means the formation or the condensation of any moisture in there into fog. So you may occasionally see that wing developing fog as it's generating lift. Perfectly normal with it. All right, let's take a peek at an airfoil where we actually start changing the angle of attack. We see smooth airflow above and beneath the wing. Now with that airfoil increasing its angle of attack, we can begin to see that the airflow is still adhering to it, but then begins to have a separation point. And we can see the turbulent flow of air from the trailing edge working its way towards the leading edge. That turbulent airflow is separation. So we have a boundary layer separation occurring. And we have the reduction of lift here, but we also have the production of more drag occurring. When we have an airfoil that reaches a greater angle of attack, it's producing more lift up until its critical angle of attack, where we have a complete separation of the airflow. We're getting to the point here where we still have a little bit of lift being developed up here in the beginning, but for the most part, we've reached that critical angle where we've now separated, and you can see all the turbulent eddies downstream from it. So only about the first 20% of that wing is producing any lift at the moment here. The rest, the airfoil has separated, boundary layer separation, and we're producing a significant amount of drag with it. So that's what's happening with your wing. When we work flaps into the picture here, flaps have the effect of kind of energizing that boundary layer for a little bit longer, allowing the aircraft to get to a greater angle of attack. So we see as that airfoil is increasing the angle of attack, we have a longer stream of smoke over it. So only the separation for about the last third of that wing has occurred at this point. So that flap has energized that boundary layer to an effect to help it attain a higher angle of attack. Some of your aircraft designs have flaps that are slotted, and we can see between the flap leading edge and the main wing there a slot, and that slot helps airflow through it to further energize the boundary layer. So just taking a peek here, you can very easily see the airfoil is hugging, or the airflow is hugging the flap there. As we increase that angle of attack, we still are developing lift back here where the flap is. We get a little bit of a separation going on, but not as much with that slotted flap. So slotted flaps are very helpful to keep that boundary layer over the wing and not cause a separation point. So that's a lot of just some quick videos on that to help you understand it. We talked about angle of attack and lift development, and we're all very familiar with the lift curve here that shows us as we increase an angle of attack, get a different color here, then we get more lift out of that airfoil. And of course, that is true up until a certain point, and that point obviously here is at the critical angle of attack. When we know at critical angle of attack, we now begin a reduction of lift. But why does an airplane stall? Right? It's interesting to note that any further increase in the angle of attack will result in less lift being developed. But here, with about a 22-degree angle of attack, you have roughly the same amount of lift developed as you do here at about 16 degrees angle of attack. That's really interesting because at 16 degrees angle of attack, I had enough lift for flight. Now suddenly at 22 degrees angle of attack, that same amount of lift, it's not enough for flight. But it really doesn't come down to the amount of lift you're developing as much as the amount of drag that's being developed. And that's what this drag curve overlay here is for, is at that 16-degree angle of attack, your drag coefficient was maybe 0.14 on it. Once we get higher, all right, we have pretty much doubled the drag output at that same angle of attack there. So it's really trying to overcome the amount of drag that's developed with the increasing angle of attack. And there's a certain point where you just don't have enough engine power to overcome the drag, because that's what opposes drag, right? The thrust you create opposes the drag that's created. So when the drag becomes too much, that's when the airplane will stall. It happens at the critical angle of attack. So really, if you could overcome that amount of drag, you could fly that airplane in a vertical profile. There are a couple aircraft that are capable of that. They have a big enough engine that they can literally point the nose straight up and go on vertical flight. There's not very many of them, but there are a couple. Let's take a peek here at further lift augmentation devices. As you get into your bigger aircraft, those aircraft have a critical wing on them, and that wing is critical that it's at a certain speed to develop enough lift for flight. Obviously, during takeoff and landing, those wings on those airliners, it's because it's a critical wing, is not producing enough lift by itself. Too slow is what's happening. So they augment that. Of course, flaps help augment it. But here's another one, a leading edge slot. You can see that slot has opened here at the beginning or leading edge of the wing. And with that slot opens, it helps to energize the boundary layer as we increase angle of attack. But we really haven't had much separation until about the last fifth of that wing there. You can still see the airflow is going through the slot and energizing the boundary layer as we go up into higher angles of attack. And close it off, we see we get earlier separation now, and a lot of lift that's been destroyed, open it back up, re-energize the boundary layer. So in some aircraft, this is very critical for their ability to take off and to land as well at that slower speed. So that's a good review of Bernoulli. Okay. The other principle with lift development is with Newton, many, many years ago, maybe centuries ago, came up with the laws of motion. Of course, we remember the first law, that an object at rest remains at rest. An object in motion remains in motion until acted on by an outside force. And of course, the second law dealt with the amount of force needed to move an object depends upon its mass times the acceleration of that object. So greater mass requires more force to move it. And the third law was for every action, there's an equal but opposite reaction. And so we think about blowing air on the underside of a piece of paper, the paper lifts up. Pretty much from the Newtonian principle, we've learned that the greater the angle of attack, the more lift we get until reaching that critical angle of attack point.